Yes?
So in this method, even if you have a shock moving around, it will pick it up? You just do this numerical integration and you will pick up the shock moving around?
Good question. If I have a shock wave moving around, I would still have the correct. So finite volume scheme works for shock waves by capturing the correct shock speed. The shape of the shock, of course, you wouldn't maintain it as a single discontinuity. The shock, as we're going to see in the next few lectures, is going to be kind of smeared. So instead of an exact discontinuity, it'll appear like this. So let's say this is the analytical solution. In finite volume, because you only approximate the volume integrals, you're going to be having average like this. Okay, I didn't draw it very well. And in this interval, you would have something more like this. And in this interval, you have something like this. So if you plot the solution as points, it will look like this. So it's kind of looks like smeared, right? And the best, the ideal finite volume scheme is this so-called one-point shock, which means you actually capture this correct behavior. There is actually, if you solve for a piecewise constant solution, there is actually only one interval that lies in between the left and right solution. That's like an ideal finite volume. And most of the finite volume schemes, especially for very complex system of equations, doesn't always have this one-point shock behavior. They may have 2 or 3 intervals within the shock wave. But the critical thing about finite volume is to correctly capture the movement of the shock wave, where it is and how fast does it move. If you zoom out this picture so that each grid point is a very small interval, it still would look like a shock wave, and it is critical to capture the location and speed of the shock wave. And finite volume does that, finite difference don't. Any other questions? All right. And I'm going to use a very simple example to illustrate how finite volume works. So that is the central flux scheme. The central flux scheme is representing U tilde U at I plus half is the average of U bar at I and U bar at I plus 1. Okay, so in Burger's equation, that means my dui dt times delta x, that's the first term in the integral form, plus half times the square of ui plus ui minus 1 minus, I think this is plus 1 because I wrote it on the left hand side, ui and ui minus 1 square is equal to 0, right? Now you get a system of equation to solve. For very different i's, the time derivative can be represented as a function of the factor of all i's. How about boundary conditions? That's easy, because if you know u at 0 is equal to 0, for example, as the boundary condition, you know that the f of u at 0 is equal to 0. So at the first interval, du1 dt times delta x would be equal to minus half of u u1 bar plus u2 bar minus half of what? 0, because here we don't need to substitute the approximation. We have the boundary condition, which is 0, right? So that's often how we apply boundary conditions for finite volume. If we know the solution there, we can directly compute the flux. Alright, so this is the simplest example of finite volume. And I'm going to warn you first, this scheme doesn't work. I mean, it's a perfectly valid finite volume scheme, but for reasons I'm going to tell you in the next lecture, this works only in smooth regions of the solution. It does not work when you have a shock wave. It is going to create numerical oscillations that looks awful, and you never want to use this scheme when you have a shock wave. And that is something special about finite volume schemes, is that when you look at the behavior of the numerical solution around shock waves, you are going to encounter constraints that you would never find in finite difference schemes. And that's what we're going to be talking about next lecture. How do you make sure a scheme is working and stable and does not create artificial oscillations near discontinuities in nonlinear conservation laws? We'll see you on Wednesday.